morning, AP. Happy day before the AP exam. I'm going to do a real quick linearization overview for you. It's probably the only thing we didn't do. Third period UDC part of this. It was the last thing we did right before we all said peace out. Sixth period you didn't see this at all. So it's a really brief concept. It wouldn't be big, like it would be a huge part of any question, but it could be part of one question. So I want to make sure I show it to you. All right. So let me flip over to my smartboard. That's not it. Oops, that was it. What is happening? Oh. There we go. Hard to remember everything. Okay, so let me zoom out a little bit. You'll be watching this on a video, so you'll be able to see it. So, linearization. Linearization, it just is that we can approximate the behavior of a function around a certain point by using the tangent line to that function at that point. Okay. The first part of this is going to be exactly what we've done in the past when we've written a tangent line equation to a function. Okay. We know we need a point and a slope in order to write a tangent line. Okay. So if we're using x equals a, then the point would be a and whatever f of a is. The slope, this is the calculus part of it, the slope is equal to the derivative of the function at that a value. Okay. And so my tangent line to f of x at x equals a would be y minus f of a equals f prime of a times x minus a. Okay. It's just, f of a is y1, a is x1, and f prime of a is the slope. Okay. Now, if you need to look at that in a little bit more concrete form, let's say the function was x squared minus 3x plus 2, and I wanted the tangent line at x equals negative 1. Okay. Well, first of all, I don't say this is y, or f of x. F of negative 1 would be 1 plus 3 plus 2. That would be 6. F prime of x would be 2x minus 3. So f prime at negative 1 would be negative 5. And so my tangent line would be y minus 6 equals negative 5 times x plus 1. Now, you may have to go back and look at that again, but essentially that is f of a, that's f prime at a, and that is the a value. Now, all linearization is about is why do we care about these tangent lines? What are tangent lines good for? We've been writing them all along. Why do we care about them? Tangent lines approximate functions. If I have a parabola that I want to work around, and I want to know a value, something on that parabola, a tangent line to the parabola very close to that point is going to be an easier function to work with. Now, a parabola is not the greatest example of this, because a parabola, you're like, well, a parabola is pretty simple to work with. You're right. But if I want to know what's happening on the function, the purple function at that black point, I can look at this tangent line. Since where the tangent line hits the curve and where the black point is are close together, this tangent line and that function curve have similar y values in this region. So the y values from the line can be estimates for the y values from the curve. Now, I'm going to show you an example of this with I'm not going to actually use this function because this is not a great, I don't know this is, but let me use, we'll go ahead and use this. So let me use this function. Let's say we want to, this is just to illustrate how it works. It's not necessarily when we would use this, but let's say we wanted to estimate 1 over 10.2. Okay. So that means I want to figure out something from this function at 10.2. Okay. What I'm going to do is I'm going to write a tangent line to 1 over x at x equals 10. Now you're saying, well, why x equals 10? Well, x equals 10. 10 is pretty close to 10.2. And so if I can figure out, if I can write a tangent line to the curve at 10, and then use the tangent line equation, the tangent line value at 10.2 is going to approximate 1 over 10.2. Now, once again, you can't judge this based on, well, I wouldn't do it that way. Well, of course you wouldn't do it that way, because we've got technology that lets us not have to do it this way. The mathematics of why that technology works has already been discussed. The calculus is the reason we can do something like this. I'm just showing you how the process works. If you were asked to do this, and we will look at an example of where you might be asked to do this, you do not have to make a decision about that. That will typically be given to you. They'll say, use the tangent line here to approximate this value. Okay. So, my f of x is 1 over x. We're doing a tangent line at x equals 10. So f of 10 is 1/10. F prime of x would be negative x to the negative 2, or negative 1 over x squared. So f prime of 10 would be negative 1 over 100. So one tangent line to f of x equals 1 over x, the tangent line at x equals 10, would look something like this. Y minus 1/10 equals negative 1 over 100, x minus 10. What we use this for then is we can say, hey, if I want a 1 over x value around x of 10, this equation can simulate that. This equation can estimate that for us. Okay. So we're going to go with, okay, I wanted to approximate what this function, what 1 over x would be at 10.2. So I'm going to put 10.2 in for x. So my minus 1/10 equals negative 1 over 100 times 0.2 So 1/10 plus negative, let's see, that would be 2/10. That's a negative 2 over 1,000, so negative 1 over 500. So a 50, so about 49 over 500. I'm gonna double check my arithmetic here real quick because I'm trying to do this kind of quick. So how about negative 1 over 100 times 0.2 plus 1/10. Yeah, 49 over 500. Okay. And if we want to look at what that value is, 49 over 500 is 0.098. If you grab your calculator and you look at 1 over 10.2, you're going to see that that's equal to 0.09803921557, blah, 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 blah. Okay. Now, it's easier to type this in the calculator than to do that linear approximation. I understand that. That's not the point. The point is, using this example is an illustration to show how the y value out of a tangent line and the y value out of the actual function can be close to each other if where we're looking for the function value is close to where we put the tangent line. This difference has to be pretty small. If we wanted to figure out 1 over 5.2 and I put a tangent line at 10, that wouldn't do a very good job. Okay, so because I wanted this, that was important to use. Okay. Now, how might you be asked to approach this? I'm going to skip ahead to this. Chances are, if you are asked to do this on your AP exam tomorrow, it will be in an abstract way. Because if it's concrete, then you can do it another way. If I want you to estimate 1 over 10.2, I don't need you to estimate that to get that. You can get that on a calculator. But if I tell you just some information about a function without giving you the function equation and then ask for an estimate, that's a whole different story. So if you're saying, well, how am I supposed to figure out f of 2.01 if I don't know what the f function is? I'm going to write a tangent line at x equals 2. And they just happen to have given me exactly the information I need so that my tangent line will let me approximate f of 2.01. This is given to be my slope. This is my point. So my tangent line would be y minus 3 equals negative 2 times x minus 2. And so then when I plug in 2.1, or excuse me, 2.01, we're going to get, and we can use a calculator for this. There's nothing against using the calculator. It's just if you don't do the calculus correct, your estimation isn't going to be acceptable. So the acceptable estimation they would be wanting is 2.98. Okay, they would be, if you're looking at it going, how am I supposed to approximate something? That's a good clue that this is a tangent line problem because they're going to give you information sort of close to your number and then ask you to find the function value of a number. Now, second part of this. Overestimate or underestimate. Is your tangent line an overestimate? Is your tangent line an underestimate? Let me go to a dual page. It's got nothing to do with knowing any more information about the original function other than knowing concavity around the tangent line. if we have a function that's concave down, and I put a tangent line to a concave down function, the tangent line is over or on top of the function, and the tangent overestimates. Okay. If we've got the alternate scenario where, because of the function being concave up, the tangent line is under f of x, the tangent underestimates. So, knowing whether what you figured out is an overestimation or underestimation has everything to do with concavity. So here is, let me undual page this. So here's the trick. F double prime of 2 is negative 5. Okay, since f double prime at 2 is negative 5, f is concave down around x equals 2. Therefore, tangent line, think about concave down, curve, overestimates. Now, if you would like to go through the rest of the problems on this handout and check answers, you're welcome to do that. Okay, so this goes over the concavity portion. Okay, so you can do example 2 and check your work. And you could do example 3, both parts, example 4, example 6, and I will have that key posted for you to double check this. Okay. Tangent line approximation, just in case it shows up. You might have a handout handy next to you while you're testing tomorrow. So if you're like, oh, wait, holy crap, how do I do that? You'll be able to access this. Okay. Good luck. Thank you.